And here we go. We're going to do some example designs for shear. And we're given this cross-section. We have floor number 8's down here. B is equal to 12 inches. D is equal to 21.5 inches. H is equal to 24 inches. And we're going to use our good old friends. The concrete compressive strength is equal to 4 kips per square inch. The yield stress is equal to 60 kips per square inch.
That's 21.5.
I'm sorry?
21, is D equal to 21.5?
Yeah, 21.5 inches. 215 inches might be one hell of a beam. All right. And then we're going to apply a shear load. And the shear is going to be equal to 12 kips, 24 kips, and 54 kips, and 77 kips. And in each case, we're going to calculate and design the shear reinforcement. So, number 1, the shear is equal to 12 kips. V sub C is equal to phi sub C, right? Or V sub N, which is equal to V sub C, and that is 0.75 multiplied by twice the square root of F prime C BD. So this is 0.75 multiplied by twice square root of 4,000 multiplied by 12 inches, which is B, 21.5 inches, which is D, and this number comes out to be
I got 12,230.
I got 24,000.
24,500 pounds, right? 24.5 kips. V sub C over 2 is equal to 12.25 kips. The demand is 12. The demand is less than the capacity. No stirrups needed. Which is pretty cool, right? No stirrups are needed. Easy. How about, what was the next one we're going to do? Number 2. Now, the shear is equal to 24 kips. That's the demand, right? V sub C is still equal to 12.25 kips. V sub C is equal to 24.5. So we're in region 2. Right? It's not, our demand is greater than V sub C over 2, but it's less than V sub C. So, where that's the case, in region 2, we need the minimum reinforcement, right? We need the minimum stirrups. So, what does that all end up looking like? Well, we said that S is equal to AS, F sub Y, divided by 0.75 root F prime C B, or D over 2, whichever is least. Because remember, this is the maximum allowable spacing. A little bit more calculation now. A sub s, we are using a number 3 bar. What's A sub s equal to? By number 3 bar. It says number 3 bar 0.11. But there's one that comes down, goes over across the bottom, and another one comes up. So a stirrup has 2 number 3 bars. So the A sub s is twice 0.11 is 0.22. We could even, if we wanted to, if that's not enough, we can always run one of these things in. This is a single leg stirrup. Right? So single leg stirrup if we needed 3, but we'll see. I think we'll be okay with 2. So if we plug this into our formula, we get 0.22 square inches multiplied by 60 KSI divided by 0.75 root F prime C B. Anyone have a number for that one? Carry the 1, right? Need to bring our abacuses in. Said the guy who left his at home. Right? There's an apocryphal story, a mechanical engineering professor who berates the students who don't have steam tables, which you use to do thermodynamic calculations, and then later on asks the students to borrow one. What'd you get? Ooh, can't be. How about that? That's a little different, right? In this case, you have to use F sub y PSI. 733? Can't be. 12.94. Anyone else? Anyone else get the same number or a different number?
Oh, so then you're using 4,000 for F prime C.
That's 4,000, yep. That sounds better. D over 2 is 21.5 over 2 is 10.75. We have to use the lesser of the two, which is 10.75. So our design is a number 3 U stirrup every 10.5 inches. Right. I can use smaller numbers. 10.5, which is 10 foot, or is it 10 and a half inches, might give me better spacing. I can go with 10 as well. It doesn't matter, okay? So that's, that was number 2. Now we do number 3. Number 3, the demand is now 54 kips. V sub c remains what value? 24.5 kips, right? So here, V sub U is bigger than V sub C we need to design steel. In fact, since V sub U is equal to phi V sub C plus phi V sub S, yep, we can go from there, and this is, we can solve that phi sub S is equal to V sub U minus phi V sub C divided by phi, which is equal to 54 less 24.5, which is, it's already got V sub C, phi in it, divided by 0.75, and that is equal to 39.3 kips. That's the load that we need to pick up. So we can get our spacing from there, right? V sub S is equal to 39.3 kips. And our spacing is given as AS F sub YD divided by the shear in the steel, because the shear force in the steel is equal to A sub S F sub Y D over S, right? And so this gives us S is equal to A sub S F sub Y D over V sub S. You heard something you don't often hear from me, which is a verbal noise. So I apologize for that. And that's equal to 0.22, right? Because I've got two number 3 bars, 60 KSI multiplied by 21.5 and divided by 39.3. Now, you have to be careful with that first equation with the square root in it, because it's a relationship. The units don't cancel out. But in this one, so long as this is in kips, this is in kips. If you want to make this 60,000, you need to make this 39,300. Piece of cake. Otherwise, and we end up with a value for our stirrup spacing at 7.26 inches. We're going to say 7 inches, right? The people were who are tying our steel are not exactly surgeons. 7.26 inches. That might be too much after a long day. No, they're not stupid. Just don't put them in a position where they can be made to look that way. D over 2 remains 10.75. So S is going to be 7 inches. And we'll go ahead, so we have number 3 stirrups, U-shaped, at 7 inches. Pretty easy, right, so far? Let's do the last one. Number 4, now our demand is 77 kips. Well, we're going to have to design stirrups, right, because we're still in region 3. V sub U is greater than V sub C, so we need to put some steel in, and the shear capacity we require of our steel is V sub U minus phi V sub C divided by phi, which is 77 minus 24.5, both of these in kips, divided by 0.75, and that gives us a shear force that we need to pick up in our steel of 70 kips. Not an inconsequential load. And we go back to our other equation, right? S is equal to ASFYD over AS FYD over V sub S, right? So S is equal to A sub S Fy D divided by that shear resistance for the steel, and that is equal to 0.22 multiplied by 60 KSI multiplied by depth D, and all of that divided by 70 kips. Anyone, yeah, that would be, if you had a number now, you'd be pretty good with your calculators, right? 4? 4.0?
Yeah, 4.05.
4.05. D over 2 is still 10.75. So we're going to use the smaller. D over 2 is 10.75. Use smaller. And we'll say our spacing is equal to 4 inches. So what's that, 4 inches? Not that close, right? Might be too close. 4 is right about there. 6 is a good number. So if we don't like 4 inches, because it seems like a lot, what can we do? Wait, we're going to redesign it. So here's our variables. Well, this is given. This is what we're trying to resist. This we figured out from flexure. So we don't want to change that. That's the steel we're using. Don't want to change that. That's the only thing we can change. Change the area of the steel. So let's say we have two options. So S is small. Increase the stirrup size. And we do two calculations here. The first is the one that the Tuesday people did, which is we're going to go to number 4, stirrups. Now our spacing is still equal to AS FYD divided by V sub S, which is 0.40, right? There's 2 legs, multiplied by 60, multiplied by 21.5, divide that by 70. What's my new spacing?
As in, 7.27.
7.27 inches. So call it 7, right? That's 7.27 inches. We're going to say that's really 7 inches. So we have number 4 stirrups, 7 inches on center. That's one method of doing it. The other is we could stick this number 3 in the middle, right? So we could have 3 legs of a number 3 bar. So instead of take this one home, instead of a U-shaped stirrup, or instead of this U-shaped stirrup here, which encloses our bars, we could have our U-shaped stirrup, plus we would add in an extra leg. And this would be a number 3 as well. So now our area of S, or area of steel, is equal to 3 times 0.11, which is 0.33 square inches, as opposed to this, where area of steel is equal to 0.22 square inches, and this, number 4 stirrup, where the area of the steel was equal to 0.40. So if we do this now, the spacing is equal to AS F sub YD divided by phi, which is 0.33 multiplied by 60 multiplied by 21.5, all divided by 0.75. And where does that take me?
You divide by.
I'm sorry?
Why are you dividing by?
I've always been dividing by phi. Oh, two. By V sub S. Good God. Thank you. Well, I've always been doing it. What are you talking about? Not only did I make a mistake, I'm sticking to my mistake.
That gives us our 6 inches.
6 inches? What is the exact number?
6.08.
6.08. Call it 6 inches. We have now made the perfect beam at 6 inches. Perfect being. That's 6.08 inches. Use 6 inches. We need one U-shaped stirrup plus 1 bent bar, all number 3s, at 6 inches. Yes, sir.
So, like from how much would that, like using the number 4s matter, both using the number 3s, like at a cost point? Is it?
That's an excellent question. It is an excellent question. Let's do that as an exercise. Okay? Let's look. What is it that does to us? That's an excellent question, and it helps me to get to our next stage. So, what's the relative cost? If I have a number 4 stirrup versus a number 3 plus a tie. Excellent question, right? So let's see, we're going to lay this out, and this distance is 21.5 inches. This distance is probably 2 inches, and this distance is 4 number 8s, so 4, 7. What did we say B was 12? So this is going to be probably 10 inches. Okay? So the total length of this stirrup is equal to 21.5 plus 2, there's 2 legs, plus 10 inches. So that's 23.5 for 47, 57 inches, right? And there's 1, 2, 3, 4 bends. If we now add in this bar, this is probably 2 inches, this is 3 inches, this is still 21.5. And this is equal to 3 and 2 is 5, 26.5 inches, right? And it has 2 bends. So option 1 is a number 4 stirrup. And that number 4 is 57 inches long. And option 2 is equal to number 3 stirrup, and and there's 4 bends. And the total length is 57 plus 26.5, and the number of bends is equal to 6, right? So let's figure it out. There's another piece of information on this table. We only ever used we only ever used 2 of them, right? We used the diameter in inches, do the bars fit? We use the area, how much load can they carry? This middle column is the weight of the bars in pounds per cubic foot. So let's check it out. The number 3 bar weighs 0.376. I'm sorry? Yeah, so I say 376 pounds per foot. And the number 4 bar is 0.668 pounds per foot. So let's figure this out, right? If we have, so in option 1, the bar is 57 inches divided by 12 inches multiplied by 0.668, and that's equal to 3.4 or something.
3.17.
Oh, really? Boo. 3.17. And in option 2, it's now 57, 77, 83 and a half divided by 12, and that's the number of feet, multiplied by 0.376.
2.62.
Now, we have to do one more calculation, right? Number 4, what did our stirrup spacing for the number 4s? Was 7 inches. Go back to the analysis. What do we get? 7 inches, right? And number 3 was 6 inches spacing. So in 42 feet, multiply these two numbers together, 42 by 12 over 6 is going to be 84 number 3 stirrups, plus the tie. 42 times 12 over 7 is going to be 72 number 4 stirrups in the same length, right? We're just on arbitrary length, and so because you can have many, many, many beams, this is just for every 42 feet of beam, this is what you require. So let's take a look. So the number 4 is equal to 84, sorry, number 4 is equal to 72, multiplied by 3.17 is how many pounds? And number 3?
220.08.
So even though they're different weights, it's not that far off, right? So what is, reinforcing steel is a commodity. It's traded, among other places, on the Chicago Mercantile Exchange. Somebody has a device that connects to the internet, type in cost of reinforcing steel, and it'll tell us what the spot cost is. Find it?
Just showing like common rebar.
Yeah, give me the cost per ton. Nah, that's boring. Cost of reinforcing steel bars.
Just showing rebar.
There it is. Cost per ton. Who cares what installation costs? Ugh.
We get like 75 cents per foot.
Yeah. It should be per pound.
Between 20 to 80 cents per pound by truckload.
Okay, so pick a number.
50 cents.
50 cents. Sounds good to me. So the rebar costs is half a dollar a pound. So the number 4 is equal to 228 multiplied by 0.50, which is $114. The number 3 is 220.8 multiplied by half a buck a pound is $110.40. A bend costs a cent. It's the steel yard tells you. So the bends, the number 3, we have 84 multiplied by 6, which is 240, 264. And the number 4 is 72 multiplied by 4, so that's 288. So this costs me an additional 264. This costs me an additional 2. Can't be. I'm sorry?
Please like that.
Yeah. Right, 84 times 6. $84 times 6 is,
504.
yeah. It's $5.04. This bending is in fact $2.88. So a total cost here is $116.88, and here it's $115.44. It's a push almost, right? But the labor to tie 84 stirrups and a tie is more than the labor to tie 72. So the materials is a wash, but the more stirrups you have, the more it costs to tie them in place. All right, well, so that's a good exercise because this is where we're headed next with beam design, which is to figure out costs. The last part of what we want to cover today is to teach you how to read hieroglyphics. Anybody like reading hieroglyphics? And I think we've covered this before, right? Have we covered? No, we haven't. How to read a bar? So you can see there's some hieroglyphics on this bar. There's some kind of crazy symbol. There's a 4. There's an S. And then if you look really carefully, do you see that second line in there? See, these are the two ridges, but there's another line here. You see that? Another line. That line tells us the strength. So this is a line card or a reference card for the or from the Concrete Reinforcing Steel Institute. I used to get them at trade shows and then give everybody one, but yeah. Anyway, you can see that this bar can be read. The first number, that funny looking hieroglyphics thing, it tells you where the mill is that the bar was made. So, that's in this case is says is H. The next bar, or the next number, is the bar size. If it's a metric bar, then it is telling you the metric number. If it's a imperial or a US bar, then it will tell you the bar number the way we use it. The third number tells you what kind of steel it's made from. So what is an S? An S is just plain old carbon steel. Anything that's carbon steel. Can't weld it. If it's a W, then it's a low alloy of steel. You can weld W bars, you can't weld S bars. You may also have R, which tells you that you have steel that meets the requirement for the railroad. You may have a T, which tells you that it meets the requirements for the railroad. You may have an A that will tell you it's made of axle steel, and each of these are definitions. They're higher quality steel. And so often a rail steel, for example, is probably 75 KSI. Axle steel probably the same. SF, stainless. And it'll also tell you if you have different types of stainless, right? Low carbon, chromium, and then which ASTM designation that it meets. And then it has a grade. And that grade can come in one of two ways. It can come directly. That bar is telling you it's a 60 KSI bar. But so is this bar, because it has this second line, this grade line. If there's no grade line and no number, then it's either 40 or 50 KSI steel, and it's probably 40. If it has 60 or a single line, then it is 60 KSI steel. 75 KSI steel will have 2 lines, or a 75. 80 KSI steel has 3 lines. 100 KSI steel has 4, depending on which requirement it meets, and 120 KSI steel will also have 4. Very rarely is it worthwhile going with higher steel strengths. So most of the steel you see in a reinforced concrete structure that doesn't need to be welded is everybody's old washing machines and cars and bookcases and, you know, other sorts of things. The parts from your transmission, well, would be melted down in a giant pot and rolled into steel almost for sure, or rolled into rebar almost for sure. Okay? Steel is the most widely recycled material in the world. No one ever has to have a drive like, we should go recycle some steel, because there's money to be made in recycling steel. So that's how you read a bar. So that's pretty good. We covered how to read a bar. I taught you how to design structures in shear. That's a hell of a lot of stuff to cover for a day. So we're going to put this recording up online, and there will be an assignment on doing some shear analysis. The only thing that is different in real beams, and we'll get to that next, is that in these beams we had that same thing. The shear goes down, it's just a point load, right? We have a big shear and then another big shear, and it's always P over 2. Sometimes it's acting in this direction, sometimes it's acting in that direction. The steel doesn't care. It always results in a tension force on that 45 degrees. If we have a beam that has, say, a uniform load across it, now our shear changes with the length. And it's foreseeable that you'll have some area of the beam close to the support that needs lots of stirrups. Then there'll be, and that'll be region 3. Then there'll be another area, part of that beam is region 2, and it won't require as many stirrups, and then you'll have a center portion where you don't need any at all. And you just approach it the same way. You write an equation for the shear, you find out when is the shear equal to V sub C over 2, and when you find where that is, then above, equal to V sub C above that, higher shear than that, you design the stirrups. The easiest way to do it is to go, typically that occurs out some distance from the edge of the support, and just make it all the same. You can make this a super cool number where you're changing the spacing each time you're supposed to tie it in. But remember, you have to build this silly thing, right? And more bars is always okay for shear. There's less bars that give you the problem. So if you calculate out here at D, D from the face of the support that you need a stirrup every 6 inches, just run that out until V is equal to V sub C. Then you pick up the minimum spacing till it's equal to V sub C over 2, then you don't need anything. The calculations are done just like this. Was there any thought process other than right at the end where we didn't like the spacing? No. It's formulaic, right? If you give me the shear, this equation will tell me these equations will tell me what my spacing has to be. And that's really what computers are for. So you can expect to do a little exercise by hand, calculate some shear calculations just like this, and then we'll move on to the computer program. Next week, we get to do deflection. And then we're done entirely with beams. I suppose you're all going to be here on Thanksgiving, right? Well, last Thanksgiving was pretty fun because I shot my own turkey. I had a 12-gauge shotgun, and I hit it twice. It was perfect. It was just standing there. It wasn't doing anything else. The people in the grocery store seemed somewhat disturbed. But I knew that turkey was dead. All right. So I will see you at least next week. Then we'll do deflection. Then you'll go off and have Thanksgiving. And when we come back, knock on wood, we'll talk about columns. All right, take care.